these are the prerequisite material notes for Calculus 1. When you come into a calculus class, it's assumed you understand some basics about trig and some mathematics, symbology. So our first page of notes here just has pictures of your various trigonometric graphs as well as their domains. You see asymptotes, periods, that sort of thing. Make sure you have a general idea of this information because you are not allowed graphing calculators or calculators of any sort on your exams in this course. The first page had the 6 trigonometric functions in their graphs. The next 3 pages have the inverse trigonometric functions. So here we have the graph of sine inverse and cosine inverse, tangent inverse and inverse cotangent, and then our inverse secant and inverse cosecant graphs as well. Please review those. If you have questions, you may certainly email me. You may certainly Google this, Khan Academy, anything, but this is material that you're supposed to have some sort of understanding when you enter this course. All right, the next page is a list of trigonometric identities that, again, I believe you should know coming into this class. Certainly, these are identities that we will use both in Cal 1 and Cal 2, and to some extent in Cal 3 as well. The reciprocal identities, most everybody knows this. If you don't particularly remember that sine is equivalent to the reciprocal of cosecant, excuse me. You certainly remember cosecant is the reciprocal of sine, so 1 over sine. Secant is 1 over cosine. Most people remember these bottom 3, but they've forgotten the relationship of the top 3. Pythagorean identities, most people remember the first, but have forgotten the second. I'd like to point out that if you remember this first identity, you could take each item in that identity and divide, for example, by cosine squared theta. So if I divide each piece by cosine squared theta, sine squared divided by cosine squared is tangent squared theta. That's just one of our rules. Cosine squared theta divided by itself is 1, and 1 divided by cosine squared theta, that's one of our reciprocal identities. 1 divided by cosine is secant, and it's being squared here. And that gives us this middle Pythagorean identity. We could do the same thing to get to our last identity there, except instead of dividing by cosine squared, we would divide everything by sine squared theta. And that would give us 1 plus cosine divided by sine is cotangent, and 1 divided by sine is cosecant, and again it's being squared. Again, that yields that last Pythagorean identity. So if you know one of them and how to get the other 2, you should be fine. But again, these are things that you're supposed to know coming in. Our quotient identities tell us that sine divided by cosine is tangent. We used that in our previous example. These double angle formulas, for sure memorize this first one. We will definitely use it in Cal 1, and you will absolutely have to use it in Cal 2. Excuse me. The power reducing half angle formulas, excuse me, power reducing half angle formulas are the same formula, but you'll call it the power reducing formula if you are trying to go from a squared function down to something that only has a power of 1. That cosine there has a power of 1 rather than the power of 2 like you see here. So we have reduced the power. If we're moving from this direction to this direction, we've reduced the power from 2 to 1. If instead we use the function in this direction, so we're going this direction, then look at what's happening here. We have a double angle that is being reduced, right? It's double angle because it says 2 times theta, and it's being halved to just a 1 theta. So depending on which direction we use, if we go from, in other words, if we start off with this in our problem and we choose to rewrite it this direction, then I will call that a half angle formula because I'm going from 2 theta down to just a 1 theta. If instead I start off with this version and choose to move this direction, then since I'm reducing the power from 2 to 1, I will call this a power reducing formula. My whole point of bringing this up is I'm pretty good about being specific with what I'm doing when I apply these formulas. So I just want you to recognize that these, these are equivalent. They're related to each other, and you'll want to make sure that you understand what I'm talking about whenever I use either the power reducing or the half angle formula. All right. The unit circle, you have to get this memorized. There are some tricks and some things I'd like to point out. I will post a video where you can use your hand to help you sort of memorize what these different values for cosine and sine are. I want to point out that in quadrant 1, which is usually what we do, we memorize quadrant 1 and then just sort of flip-flop it and mirror image it to get anything in quadrant 2 or quadrant 3 or quadrant 4, which is down here. So if I'm thinking of just quadrant 1, I want to remind you of a few things. In calculus, we always use radians. We do not use degrees. So if you're used to saying 30 degrees or 45 degrees or 60 degrees, we're not doing that. Right? You're going to use radians. So this would be 0 or 2 pi, depending on what you're doing with the problem. This would be pi over 6, pi over 4, pi over 3, pi over 2. And then I want to point out that there is a pattern. And it's a little hard to see because of the way this is laid out. But if you think of each of these coordinate pairs, we could write every single x and y value for each of these coordinate pairs as being a numerator over the number 2. For example, instead of writing this as 1, 0, I could write this as 2 divided by 2, 0 divided by 2. Those are equivalent statements. 2 divided by 2 is 1, 0 divided by 2 is 0. Now you may think, why is she doing this? This actually helps with my pattern, so let's just hang on to that guy. I'm going to write this one in a sort of vertical format, so square root of 3 over 2 and 1 over 2. Same thing with this one. I want to point out that all of these are some number over 2. I also notice that for these guys, I've got some square roots. So I'm wondering if I could maybe impose a square root everywhere to really make my pattern stand out. And sure enough, I think I can. Instead of writing this as 2 divided by 2, maybe I could write it as square root of 4 divided by 2. That would be the same, wouldn't it? That would still give me 2 divided by 2, and 2 divided by 2 is 1. And we would have, I could even do square root of 0 over 2, because I know square root of 0 is 0, and 0 divided by 2 is 0. So I'm tweaking this just a little bit more, and I'm going to write this as the square root of 0 over 2 and the square root of 4 over 2, and make a mental note that that's equivalent to the 0, 1 of my coordinate pair. I could do the same thing down here. Square root of 4 divided by 2, square root of 0 divided by 2. I could even do it with the number 1, right? Because the square root of 1 is 1, so the square root of 1 over 2 is equivalent to this guy. Make sure you believe that. That's the good thing about videos, is you can pause and go back. So I think that I'm just about done, and I'm wondering if you see the pattern yet. If you don't, let's see if we can make it a little more obvious. The square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. And then I go the opposite direction, right back down the circle. So square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Remember that your first coordinate, the first number in your coordinate pair is an x, and the second number in the coordinate pair is a y. And it really doesn't matter how quickly you can do this, just as long as you can do it. So when you sit down to take your exam, in the top left-hand corner of the first page, if you can quickly regurgitate this, you ought to be okay. Now, whenever you write it, I would want the simplified form. So I don't want to see square root of 0 over 2. I would want you to actually write that as 0. And we don't really want to see square root of 4 over 2. We know that the square root of 4 is 2. We know that when you divide it by 2, you get 1. So I'd actually want to see the most simplified version of it. But still, this ought to give you some method of remembering. Remember that x values correspond to the cosine. So x values correspond to the cosine of the angle, and y values correspond to the sine of the angle. So if I asked you, what is sine of pi over 6, here's pi over 6, sine is the y value. Yikes, I pointed to the wrong one. Sorry. Sine is the y value, and you would tell me square root of 1 is 1 over 2. All right, the last page is this sort of prerequisite stuff. You may not have seen this quite as much or used it as often as you have the previous pages, but I feel like I need to include it because I do use the mathematical symbols. And this is just a list of all the mathematical symbols that you might see in this class. Some important ones are the approximately symbol, sort of a squiggly equal sign, does not equal, The phrase does not in mathematics is usually a slash through whatever you're saying does not occur. So if it does not equal something, you put a slash through the equal sign. This is defined to be, it's 3 bars. It is not equivalent to the equal sign. In fact, I have only seen in all the mathematics courses I've taken, I have only seen this symbol used once. There are occasions when some mathematicians might define for example, factorials. If you recall 5 factorial, that's 5 times 4 times 3 times 2 times 1. Generally, whatever number you have, factorial, is you start off with that number. It's usually a natural number, right? You start off with that number and you multiply it by every number smaller than it until you get to the number 1. Okay, well, on occasion, you will see some mathematicians take the number 0 factorial, and maybe they need it for a proof or something like that. Some mathematicians will say 0 factorial is defined to be 0. Others, because of the way they're using it, say it's defined to be 1. This is the only time I have ever seen this triple bar used. Please do not use it as if it's an equal sign. It's wrong. I'll take off points, so be very careful. And by the way, if I ever say, hey, don't do this, I'm going to take off points, that means someone before you has done it, and I've had to explain to them that, no, that's not the correct meaning or whatever. And so I'm just forewarning you. Don't take it as I'm mad or anything like that. I'm just forewarning you. You don't want to do that, so learn from other people's mistakes. All right, some students will use this symbol as if it's an equal sign. Yikes, no way, man. No way. Arrows are not equivalent to equals. Nope. No. Don't do that. You're going to get points taken off, all right? This actually means approaches or maps to. Those are the actual phrases. So you wouldn't want to say 3 plus 4 maps to 7. That doesn't make sense. 3 plus 4 approaches 7. No, 3 plus 4 actually is 7. So use the correct symbols here, and I'm always very good about telling you when to use what, right? So just make sure you try to retain that. All right, some others that we use, this triangle where with the pointing upward triangle, I guess that's the way to say it, means therefore. If the triangle is sort of pointing downward, it means because. This upside down capital A, it means for all. All right, so this is just shorthand for mathematicians. Remember that the purpose of this is so that if you're a mathematician in, say, Mexico, and you're trying to speak to a mathematician in China, right, you don't have to worry about there being a language barrier because you both understand these symbols. This is an element of, so we might say something like 3 is an element of the integers, or 3 is an element of all real numbers. Union means you can lump the two sets together. Intersection is what do the two sets have in common. And here we have the double bar letters for our different types of numbers. All real numbers is anything that is not an imaginary number, right? Set of all integers. Integers are positive and negative whole numbers. So -3, -2, -1, 0, 1, 2, 3, and it goes on forever in both directions. Rational numbers can be written as a fraction. The set of all natural numbers. Natural numbers are your counting numbers. Remember when we first, as a human race, right, started discovering numbers, we didn't actually understand the concept of zero. Probably some dude was hanging out with his sheep saying, okay, I have 1 sheep, 2 sheep, 3 sheep, so forth and so on, right? He didn't, the day before, contemplate the fact that he had no sheep, right? So the number 0 is not actually a part of the natural numbers. So the natural numbers start at 1 and go on forever. Sometimes they're called counting numbers, but remember, the natural numbers start at 1. The whole numbers are all the natural numbers, and I don't have the whole numbers listed here, but the whole numbers are a double bar W, and they would be all the natural numbers and the number 0. Okay, so hang on to these things, just keep it in your notes and you can reference it, make sure you understand. The unit circle is probably the most important thing there, and then the trig graphs and the identities.